Dear students, welcome to the session. Today we are going to discuss introduction to multiplexers. This multiplexers sometimes we can call it as MUX. Means instead of using the term multiplexers we can also call it as MUX. Now we'll see what is a multiplexer and why we are using this multiplexer and how can we design this multiplexer. Okay. First, I'll tell you what is a multiplexer. Multiplexer is a combinational circuit which consists of many input lines and directs to or sends to single output line. Okay. Here the definition is what? It is a combinational circuit, right? Then it is having a many input lines and out of all lines it will send only single output line. This multiplexer I can represent with one block diagram like this. We can call it as block. This block represent MUX. As I already told you, it has many input lines, right? So those input lines I will consider as, let's take I1, I2, I3 till IN, right? But it has a single output line. Let's take Y as a output line. These are all input lines. From the definition, it always directs single input line to the output. Means at every instant will have only one value as output. Means for a while, for the first input, for the first instance, we'll consider only I1 data is transferred to the Y. Similarly, for the next instant, I2 data will transfer to the Y. Next, I3 may be transferred to the Y, like that. But every instant, only one input line is directs to output line. Then how can it transfer? Like how can it selects output this input lines? Right. So in a multiplexer, in addition to the input lines and output lines, we'll have one more line called selection lines. Okay. Based on combination of these selection lines, only the input data is transferred to Y. Means for one particular combination of selection line, I1 data is transferred. Similarly, for the next combination of selection line, I2 data will be transferred. Similarly, for the next combination, I3 will be transferred. So from this, I can say that the more specifically, the definition is, it is a combinational circuit which consists of many input line and directs to a single output line with the help of or by using with the help of selection lines. Right? Fine. Now we came to know what is the multiplexer. Now, what are the different types of multiplexers we need to see and how we can implement, that is also we need to see, right? Here, the types are always based on number of input lines. That is, if you are having input lines are 2, then we can call it as 2 input lines, single output line. Then the type will be 2 cross 1 mux, right? If for a while, if the input lines are 4, then the type will be 4 cross 1 mux, right? If the input lines are 8, then it will be 8 cross 1 mux. If the input lines are 16, then it will be 16 cross 1 mux. If the input lines are 32, then we'll have 32 cross 1 mux. Similarly, if the input lines are 64, 128, 256, like that, right? See, either it may be a 2 cross 1, 4 cross 1, 8 cross 1, or whatever it is. Only input lines are changing. But output is always single output, right? This combination gives input-output relation. 2 means input lines, 1 is the output line. So 2 input line, 1 output line, mux. Here 4 input line, 1 output line, mux. Right? Similarly, 8 input line, 1 output line, mux, like that. Fine. But as we know, out of all these inputs, at every instant we'll select only one data as output. For that, we require selection lines also. Now the thing is, what is the number of selection lines is required for this muxes, right? For that, there is a one relation between number of input lines and selection lines. There is a relation, that is n equal to 2 cross m. This is a relation between input lines and selection line, where n is number of input lines and m is number of selection lines required. Okay, n is number of input lines and m is number of selection lines. Now we know the number of input lines. These are our number of input lines, right? So if input lines are 2, n is 2. So to satisfy this equation, m value must be equal to 1, right? So from this 2 cross 1 mux, the selection lines will be 1. For the next case, just see, if the input lines are 4 here, right? If input lines are 4, to satisfy this 4 value means n value, we can write 4 as 2 square, right? So then what is the m value here? Then m is 2. Similarly, 8 we can write as 2 cube, right? So for this case, m value is 3, nothing but selection lines are 3. Here, if input lines are 16, means n is 16, that 16 we can represent 2 power of 4, right? So m here will be 4. Similarly, 32 we can write like a 2 power 5, so the selection lines will be 5. Like that, by using this relation, we can find the number of selection lines for each mux, right? Now, till now we came to know what is a multiplexer and what are the types of this multiplexer. Now we'll see what are the applications of these multiplexers. By using these multiplexers, we can implement adders. Adder means either it may be a full adder or it may be a half adder. Similarly, subtractors, like either it may be a full adder, a full subtractor or half subtractor, or many combinational circuits also. Right? These are the some of the examples for multiplexers. Then now the thing is, as we already know how can we implement like adder and subtractor? Then why we are going for this multiplexer? The thing is, when we are using the mux, by using mux, the advantage, a very important advantage is number of gates gets reduced. Though we can implement this adder by using basic gates or functional gates, now when we are using with the multiplexer, the very important thing is the gates required to implement adder or subtractor or any combinational circuits will get reduced. That is the first advantage of this mux. So as we know, what will happen when gates are reduced? When the gates are reduced, obviously the complexity of circuit is reduced. So this is the second advantages. These are the advantages of mux, right? First thing is what? By using mux for the implementation of adder or any combinational circuit, gates will be reduced. When the gates are reduced, complexity of particular circuit is reduced. And the same thing, when gates are reduced, number of gates reduced, cost is also reduced, right? These are the some of advantages of multiplexers, right? Now we'll implement all the multiplexers by using logic gates. First we'll design 2 cross 1 multiplexer, or we can call it as 2 cross 1 mux, right? As multiplexer is a combinational circuit, we can represent with a block diagram like this. 2 cross 1 mux. What it sends? 2 means the number of input lines. So I will consider 2 input lines. Let's take I0 and I1. 1 is the output line. So Y is my output line, which is single, right? So to direct input as a output in a multiplexer, we require a selection lines, right? These are the input lines, and this is output line. Along with input and output, the third thing is what? Selection lines. As we have a relation, what it is? N equal to 2 power m, right? As input line is 2 power m, we can write it as 2 power 1. So this 1 is nothing but the selection lines required value. So as it is 1, we require 1 selection line. Let's take yes. Okay. Now the thing is, we need to design the logic diagram which is there in this block diagram. That we require. As we know, whenever we wanted to implement a logic diagram, okay, to implement the logic diagram, first we require logic expression. And logic expression is always obtained from the relation of inputs and output, that is nothing but truth table. So from this, first we need to get the truth table. Then from the truth table, we can develop logic expression. From the logic expression, we can find the logic diagram, right? So first I'll design, find the truth table for this circuit. Right? Generally, for the multiplexers, in addition to the input line, output line, select lines, there is a one more additional input is there, that is called enable. Okay? By using these two values, we can direct the input values. So one is E, the next one is S. We want Y output. Okay. For the first case, I'll consider this enable value is 0. Right? When enable is 0 means during this particular case, irrespective of the remaining, like whatever may be the selection line, whatever may be the input, your output is always 0 itself. Means this multiplexer is in off condition when enable is 0. So I can say that when enable is 0, irrespective of selection line value, directly your output will be 0. Right? So that is one possible case. For the next remaining cases, I'll make enable value as 1. Right? So when enable is 1 and S is 0. So enable once means this is an on condition. Now we'll change the selection value so that the output, the input transfer to the output will change. So when S is 0, I0 will be transferred to the Y. So your output will be, Y is nothing but whatever the data which is exist in I0. For the next case, again I will continue with E as 1, means your circuit is in on. I will make S as 1. So when S equal to 1, I1 will be transferred to the Y. So here output is I1. Now I know the logic truth table for this mux. So from this truth table, we need to find the logic diagram. Right? When we are developing when we are writing the logic diagram, we'll always consider only output values are high. Right? So I'll consider Y, this is logic expression. See, I am considering here SOP form. So I can write this output value as E value is 1. So directly I am writing E. S 0. So 0 means I can write this is in complemented form S bar, and output is what? I0. So this is one possibility to get the output. So E S bar I0, or you may get this is also as an output, right? So I can write E S bar I0, or one more is what? E S is an uncomplemented form. So S, and this is I1. Now in this logic expression, E as common, take E as common, we can write S bar I0 plus S I1. Right? Now we know the logic expression for this 2 cross 1 mux. Once you know the logic expression, then we can develop logic diagram. To draw the logic diagram, consider all the inputs which are exist here. Here we are considering selection line as a one input, right? And one more input is what? I0, and one is I1. Okay. So I'll implement this, which is what? Here we are having two product terms. So two AND gates are required. So first I am considering one AND gate where the inputs are E. So I'll take one more input as E. We'll consider it as E. We'll give the common input later. I'll give only these terms, which are what? S bar is required. See here, S bar is required. So give selection line input to one NOT gate so that you will get the S bar value. S bar I0 I naught and S bar, which is ORed with Si1. So we'll require one more AND gate. Here these inputs are S and I1. For these two gates, E is common. So I am taking E value. This is E. And here one important thing is E is always 1 itself. Right? So I am fixing here E value as 1. Now, these two values are ORed together. Give it to 1. OR gate to get the logic expression Y. See, first term is, here it is, S bar, see S bar, I naught, and one more input is E. This one is S, I1 and E. These two are ORed, so I am giving one OR gate and the Y. Y is the output output of this 2 cross 1 mux. So now the inbuilt circuit in this block is nothing but this circuit diagram or logic diagram. Okay.